For the purposes of computing determinants of some small matrices by hand, it turns out there's a more efficient algorithm we can use that we call cofactor expansion. The method is recursive and relies on the following definition. So we're going to start out with an n by n matrix A, whose entries are the aij's. We define the minor of the entry aij to be the following n minus 1 by n minus 1 matrix, which is obtained by deleting row I and column j from the matrix A. While the notation in the definition might seem unwieldy, this is not a difficult thing in practice to understand. So let's take the following 3 by 3 matrix. To find the minor of the entry A22, we'll simply delete row 2 and column 2 from A. And we're going to denote this matrix M22 to indicate that it is the minor of the entry in the second row and second column. For a slightly larger example, we could try a 4 by 4 matrix. If we want to find the minor entry for A31, we simply need to take our matrix, delete row 3 and column 1. So to describe the cofactor expansion algorithm, we're going to use these minors to compute what is called the cofactor of an entry. The cofactor of the entry aij is the number which we call cij, which is -1 raised to the I plus j power multiplied by the determinant of the minor of aij. So as an example, let's go back to our first 3 by 3 matrix, which was 1 minus 2, 3, -1, 2, minus 1, 2, -6, 10. If we want to compute the cofactor of entry A22 for the matrix, we take -1, raise it to the 2 plus 2 power, and then multiply it by the determinant of M22, which we found was the matrix 1, 3, 2, 10. And we can use the formula from the end of the previous video to see that this is 10 minus 6 is equal to 4. So the cofactor for the entry A22 is 4. So this is where the recursive piece of this comes into play. In order to be able to compute the determinant for a 3 by 3 matrix, we need to be able to compute determinants for 2 by 2 matrices. Once we know how to compute the determinant of a 3 by 3, we'll be able to use that to compute determinants for 4 by 4 matrices. This algorithm is called the cofactor expansion algorithm. It works on any n by n matrix using one of the 2 following methods. First, fix any row I. The determinant of A is the sum from j equals 1 to n of the entry aij multiplied by the cofactor of the entry aij, which is the same thing as the sum from 1 to n of -1 to the I plus j aij multiplied by the determinant of mij. Alternatively, we can fix a column j and perform a similar sum. Note here that there's a subtle difference between these 2 formulas, which is actually very important. In the first sum, the index is j. That means we are working across the columns j. In the second sum, the index is I. In this case, we're working across the rows. In practice, one most commonly uses the first row, so the determinant is computed as the following alternating sum. So to exemplify this, let's compute the determinant of our 3 by 3 matrix. So using the cofactor expansion, with the first row, we see that the determinant of A is the determinant of M11 plus the determinant of M12 plus twice the determinant of M13. The determinant of our first matrix is 20 minus 6. The second is negative 20 minus negative 18. And the third is 2 minus 6. That gives us 14 minus 2 minus 8, which is positive 4. So there is the determinant of this 3 by 3 matrix. So it's important to note that this method is extremely unwieldy for larger matrices. For even a 4 by 4 matrix, this can be really tricky since it requires computing the determinant of 4 3 by 3 matrices. To compute each of these 3 by 3 determinants, we'll need to compute 3 2 by 2 determinants, and each 2 by 2 determinant requires computing 2 products. In the end, this results in performing 4 factorial or 24 computations. If you're thinking about this in terms of algorithms, the computational complexity for the cofactor expansion is roughly n factorial. And if you know anything about computational complexity, this is really bad. So to see why it is important to be able to choose the minors in the cofactor expansion, let's compute the determinant of the following matrix. So as we observed before, if we use the entries along the top row, our determinant computation would end up roughly around 24 computations. However, we can use a different row, or even potentially a column, to make our computations much simpler. So let's use the bottom row for our cofactor expansion. We'll see that 3 out of the 4 determinants that we would normally have to compute have a coefficient of 0. That means we only have to compute one determinant. Now, faced with the determinant of a 3 by 3 matrix, we make the same observation. If we choose to do our cofactor expansion using the bottom row, then we only have to compute the cofactor corresponding to the bottom right-hand entry. And now that we've reduced this to a 2 by 2 matrix, we can see that the determinant is going to be 2 multiplied by 3 multiplied by 4. In fact, you could use this to see that to compute the determinant for an upper triangular matrix, or symmetrically a lower triangular matrix, you simply need to multiply the entries along the diagonal. So this observation brings us to an interesting point about why anyone cares about the determinant of a matrix. So recall that in our last video, we saw that we can use Gaussian elimination to compute determinants for matrices. If B is the reduced row echelon form of our matrix A, and we encode the row operations to get from A to B as the matrices E1 through En, then we can write En times En minus 1 times dot 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 times E2 times E1 times A is row equivalent to B. In fact, is actually equal to B. This tells us that the determinant of B is the determinant of En times the determinant of En minus 1 times etc. the determinant of E2 times the determinant of E1 times the determinant of A is equal to the determinant of B. Now, this is interesting because the reduced row echelon form is always, by definition, an upper triangular matrix. So that tells us that if our reduced row echelon form does not have a leading entry in at least one of the columns, it will have a 0 along the diagonal. Our previous observation tells us that the determinant of such a matrix is necessarily 0. So this tells us that the determinant of A is non-zero if and only if its reduced row echelon form has a 1 in every slot on the diagonal. But of course that tells us that the matrix B, that's our reduced row echelon form for A, must be the identity matrix in order for the determinant to be non-zero. So we have proven that the matrix A is invertible if and only if its determinant is non-zero. And as a cute little corollary, we can actually compute for an invertible matrix the determinant of its inverse with no work whatsoever. We simply take the product A inverse is equal to the identity matrix I. Take the determinant of both sides, then use the fact that the determinant is a multiplicative function to split this into two determinants on the left. Then divide both sides by the determinant of A, and we have now shown that the determinant of A inverse is 1 over the determinant of A. And that's it for determinants.